Hello students, welcome to another video of number theory. In previous video, we have seen that Euler's generalization of Fermat's theorem, and today we are going to see the Fermat's theorem. So let's start the Fermat's theorem. Fermat's theorem. Fermat's theorem states that statement of the Fermat's theorem is, let P denote a prime. Let P denote a prime. P denote a prime such that GCD of A and P is equals to 1. So that GCD of A and P is equals to 1. Then A raised to P minus 1 is congruent to 1 mod P. A raised to P minus 1 is congruent to 1 mod P, or we can say that A raised to P is congruent to A mod P. A raised to P is congruent to A mod P. Statement says that let P be a prime and GCD of A and P is equals to 1. Then we have to prove that A raised to P minus 1 is congruent to 1 mod P, or A raised to P is congruent to A mod P. So in the proof, we have seen the Euler's generalization of Fermat's theorem, and the statement of Euler's generalization of Fermat's theorem is GCD of A and M is 1, then A raised to phi of M is congruent to 1 mod M. So we are going to use that result here. Here P be a prime number, we have given P be a prime number, P be a prime number, and GCD of A with P, GCD of A and P is equals to 1. So we can use we can use Euler's generalization of Fermat's theorem. Euler's generalization of Fermat's theorem says us GCD of A and M is equals to 1. GCD of A and M is equals to 1. Then A raised to phi of M is congruent to 1 mod M. Therefore, by using Euler's generalization of Fermat's theorem. Euler's generalization of Fermat's theorem. Therefore, by using Euler's generalization of Fermat's theorem, we can write A raised to phi of P. Here instead of M there is P. So A raised to phi of P is congruent to 1 mod P. A raised to phi of P is congruent to 1 mod P, but phi of P is equals to P minus 1 we have seen in Euler's phi function, that is if P is prime then phi of P is P minus 1. Therefore, we get A raised to P minus 1 is congruent to 1 mod P. A raised to P minus 1 is congruent to 1 mod P. This is since phi of P is equals to P minus 1 for any prime number P. So we get A raised to P minus 1 is congruent to 1 mod P, or we have to say that A raised to P is congruent to A mod P. So multiplying both sides by A, we get multiplying both sides by A, we get A raised to P minus 1 into A is congruent to A under modulo P. A raised to P minus 1 is congruent to A modulo P. So multiplying by this A, we get A raised to P is congruent to A mod P. A raised to P is congruent to A mod P. Hence the proof of Fermat's theorem. Hence the proof. So Fermat's theorem the statement of the Fermat theorem is, if P is prime and GCD of A and P is equals to 1, then A raised to P minus 1 is congruent to 1 mod P, or A raised to P is congruent to A mod P. To prove this result, we have given GCD of A and P is equals to 1. So we can use the Euler's generalization of Fermat theorem, and Euler's generalization of Fermat theorem says us A raised to phi of m is congruent to 1 mod m. Here m is equals to P and P is prime, so A raised to phi of P is congruent to 1 mod P, and we know that the value of phi of P, that is the integers which are less than P and relatively prime to P, are exactly P minus 1 since P is prime. So A raised to phi of P is congruent to 1 mod of P gives us A raised to P minus 1 is congruent to 1 mod P. So multiplying both sides we get A raised to P minus 1 into P, or A raised to P minus 1 into A, and A raised to P minus 1 into A is A raised to P is congruent to A mod P, hence the proof. In the examination, the questions will be state and prove Fermat's theorem, so you must know this statement. So now we are going to discuss some examples. First of all, take the example, find the remainder. Examples on Euler's generalization of Fermat's theorem and Fermat's theorem. Find the remainder. Find the remainder when 4 raised to 37 plus 82 is divided by 4 raised to 37 plus 82 is divided by 7 is divided by 7. If you divide this number by 7, so what will be the remainder that we are going to find? So in the solution, we know that Euler's generalization of Fermat's theorem is A raised to phi of m is congruent to 1 mod m. So using that result, or we can simply say that here we are dividing this number by 7. So in the Euler generalization of Fermat's theorem, we were dividing this, we are dividing here, we are dividing A raised to phi of m by m. So here m must be 7. So let m is equals to 7, and the statement of Euler generalization of Fermat's theorem is A raised to phi of m. So if we take A is equals to 4 here and A is equals to 4 using the Euler generalization of Fermat's theorem, or we can simply use the Fermat's theorem, since this m is equals to 7 is prime number. Therefore by Fermat's theorem, we get statement of Fermat's theorem is A raised to phi of P is congruent to, this is the statement of Euler generalization of Fermat's theorem, and the Fermat's theorem gives us A raised to P minus 1 is congruent to 1 mod P. So here P is 7 and A is 4. So we use A raised to P minus 1, that is 4 raised to 7 minus 1 is 6 is congruent to 1 modulo 7. That is, if we divide this number by 7, we get remainder 1. So from this congruence, we are going to find this 4 raised to 37 plus 82 is divided by 7. We are going to find the remainder when this number is divided by 7. So here 4 raised to 6, but we want 4 raised to 37. If we raise the power of this term by 6, we get 4 raised to 6 to the power 6 is congruent to 1 raised to 6, taking 6th power on both sides, that is 1 raised to 6 modulo 7. So 4 raised to 6 into 6 is 36. So 4 raised to 36 is congruent to 1, 6 power of 1 is 1 under modulo 7. So we get 4 raised to 36 is congruent to 1 modulo 7. 36 is near to 37. So if we multiply both sides by 4, we get 4 raised to 37 is congruent to 4 modulo 7. Multiplying both sides by 4, we get, therefore multiplying both sides by 4, we get 4 raised to 36 into 4 is congruent to 4 into 1, that is this into 1 under modulo 7, that is 4 raised to 37 is congruent to 4 modulo 7. Suppose this is equation number 1. So we want to find the remainder when 4 raised to 37 plus 82 is divided by 7. So we will find first of all where 82. If we divide 82 by 7, then we are going to find the remainder. So if we divide this 82 by 7, we get the remainder 17 are 77 are 77. So we get remainder 5. That is, if we divide 82 by 7, we get remainder 5. That is 82 minus 5 is equals to 77, and 7 divides 77. So we get remainder 5. This is equation number 2. So adding equation 1 and 2, we get 4 raised to 37 plus 82 is congruent to 5 plus 4, that is 4 plus 5 modulo 7, which is congruent to 4 plus 5 is congruent to 9 modulo 7, but 9 under modulo 7 is congruent to 2 modulo 7. So 4 raised to 37 plus 82 is congruent to 2 modulo 7. Hence we get the remainder 2. This is the remainder 2 when this 4 raised to 37 plus 82 is divided by 7. So first of all, by using Fermat's theorem, we get 4 raised to 6 is congruent to 1 mod 7, and raising the power by 6, we get 4 raised to 36 is congruent to 1 mod 7. So multiplying both sides by 4, we get 4 raised to 37 is congruent to 4 mod 7. So taking this equation 1 and we are adding both sides by 82, we get this, or taking separately 82 is congruent to 5 modulo 7, and adding these two, we get 4 raised to 37 plus 82 is congruent to 4 plus 5 modulo 7, but 4 plus 5 is 9. If we divide any number by 7, then we must get remainder less than 7. Here 9 is greater than 7. So this 9 is congruent to 2 modulo 7. So 2 is the remainder when 4 raised to 37 plus 82 is divided by 7. So this is the solution, that is this 2 is remainder. Another example that we are going to take in. Another example is what is the, or find the last digit. What is the last digit in the ordinary decimal representation? In the ordinary decimal representation, ordinary decimal representation of what is the last digit in the ordinary decimal representation of 3 raised to 400. So this is the question, what is the last digit in the ordinary decimal representation of 3 raised to 400? To solve such problems, we must know what we have given. Here we have given that is we have to find the last digit of ordinary decimal representation of 3 raised to 400. If we write this 3 raised to 400 in decimal representation, decimal means if you divide this number by decimal means 10. If you divide 3 raised to 400 by 10, then we have to find the remainder. So if we want to find the last digit in the ordinary decimal representation of this number, we must divide this number by 10. That is, decimal means if we divide this number by 10, then the remainder is the last digit in the ordinary decimal representation of 3 raised to 400. So here we are dividing this number by 10. So our the value of m is 10. Here m is equals to 10 and we are dividing 3 raised to 400. So a raised to something. So the value of a is 3. A is equals to 3. So here m is equals to 10 is not prime number. So we can't use the Fermat's theorem. So we have to use the Euler's generalization of Fermat's theorem. Euler's generalization of Fermat's theorem. Therefore, by Euler's generalization of Fermat's theorem, Euler's generalization of Fermat's theorem, we have a raised to phi of m is congruent to 1 modulo m. So here m is equals to 10 and a is equals to 3. So we can write 3 raised to phi of 10 is congruent to 1 modulo m, and we know that phi of 10 is 4, since there are only 4 integers which are relatively prime to 10, which are 1, 3 and 1, 3. After that 7 and 9. So these 4 integers are relatively prime to 10. So phi of 10 is 4, or we can find the phi of 10 by writing 10 into canonical form, that is 2 into 5. So 10 into 1 minus 1 by 2 into 1 minus 1 by 5. After that calculations we get phi of 10 is equals to 4. So this is the value of phi of 10 is 4, is 3 raised to 4 is congruent to 1 mod value of m is 10. So here must be 10, 1 modulo 10. Now raising the power of both side by 100, we get 3 raised to 400 is congruent to 1 raised to 400 modulo 10. This gives us 3 raised to 4 to the power 100 is congruent to 1 to the power 100 under modulo 10. So 3 raised to 4 into 100 is 400. This gives us 3 raised to 400 is congruent to 1 raised to 100 is 1 modulo 10. Then this is the last digit in the ordinary decimal representation of 3 raised to 400. Therefore 1 is the last digit. 1 is the last digit. 1 is the last digit in the ordinary decimal representation. In the ordinary decimal representation of 3 raised to 400. If you are given such a problem, that is find the last digit in the ordinary decimal representation of something raised to another thing, then we must divide that number, that power by that number, that is 3 raised to 400 by 10, and the remainder is our last digit. And another example for your homework is, what is the last digit in the ordinary decimal representation? Homework is same question for 7 raised to 400. 7 raised to 400 is homework. Now we are going to take another example. List all the integers. Another example. List all the integers. X. List all the integers x such that x must be congruent to 7 under modulo 17. That list all the integers x such that x is congruent to 7 modulo 17, and this x must be less than, that is x must be 1 to 100. Find the all integers in between 1 to 100 which satisfies this congruence. We have to list all the integers in between 1 to 100 which satisfies this congruence. This is one of the simplest example and can be asked for 2 marks. We have given that is we have to find the all x such that x is congruent to 7 mod 17. Since we have to find the x such that x is congruent to 7 mod 17. Therefore, for on this congruence using the definition, therefore by definition of congruence, we can say that 7 divides x minus 7, sorry, 17 divides x minus 7, 17 divides x minus 7. So therefore by using definition of divisibility on this term, using definition of divisibility, we can write x minus 7 is equals to 17 into k, where this k is an integer, so we get this equation from this congruent. So x minus 7 is equals to 17k, and we are going to find the values of x which satisfies this congruent. So from this, rearranging this, we get x is equals to 17k plus 7, adding 7 on both sides, we get x is equals to 17k plus 7, where this k is an integer, so to find the integers in between 1 to 100, we must get the values from 1 to 100, and that x must satisfy this congruent, that is x must be of this form. So if we take the value of k is equals to suppose 0, then we get 17 into 0 is 0 plus 7 is 7. So 7 is in between 1 to 100. So we get the value of x is equals to 7, we satisfy this congruency. 7 is congruent to 7 modulo m, 7 modulo 17, since 17 divides 7 minus 7, 0. So we get first number as 7. If we put the value of k is equals to 1, then we get 17 plus 7 is 24. K is equals to 2, k is equals to f. Substituting these values, we get answer. If we put k is equals to minus 1, then we get minus 17 plus 7 is minus 10, and minus 10 is not in between 1 to 100. So we must put the values of k from 0, 1 and 2. Therefore, putting k is equals to 0 in this suppose equation star, we get x is equals to 7. Now putting k is equals to 1 in equation star, we get x is equals to 17 plus 7, and 17 plus 7 is 24. So 24 is again in between 1 to 100. Now putting k is equals to 2 in star, we get x is equals to 17 into 2 plus 7, that is 17 into 2 is 34 plus 7. So 34 plus 7 gives 41. So 41, again 41 is congruent to 7 modulo, since 41 minus 7 is 34, and 17 divides 34. Another value is 41. So now putting k is equals to 3, we get x is equals to 17 into 3 plus 7. 17 3 is 51 plus 7 is 58. Now putting k is equals to 4, we get x is equals to 17 into 4 plus 7, which is equals to 17 4 is 68 plus 7, which is equals to 75. Now another time putting k is equals to 5, we get x is equals to 17 into 5 plus 7. 17 5 is 85 plus 7 is 92. So if we divide 92 by 7, we get 7 as a remainder. Then after putting the value of k is equals to 6, we get the number x greater than 100. Therefore the integers are 7, 24, then 41, then 58, after that 75 and 92 are the integers, the integers are the integers x, are the integers x in between 1 to 100, such that x is congruent to 7 modulo 17. Hence the solution of this example.